US Physics Olympiad, year 2012, USAPHO Semifinal Exam. Problem A3. Solution for this problem you can find in the reference of the description below this video. Two infinitely long concentric hollow cylinders have radii A and 4A. Both cylinders are insulators. The inner cylinder has a uniformly distributed charge per length of plus lambda. The outer cylinder has a uniformly distributed charge per length of negative lambda. An infinitely long dielectric cylinder with a permittivity epsilon equal K epsilon 0, where K is the dielectric constant, has inner radius 2A and outer radius 3A. Is also concentric with the insulating cylinders. The dielectric cylinder is rotating about its axis with an angular velocity omega much less than c over a, where c is the speed of light. Assume that the permeability of the dielectric cylinder and the space between the cylinders is that of free space, μ0. Question A. Determine the electric field for all regions. Question B. Determine the magnetic field for all regions. Solution. Question A. For this question we can use a regular problem for infinite wire with a uniformly distributed linear charge with a linear charge density lambda. We can construct a Gaussian cylinder with the length L and concentric with this construction with the radius R. So for this cylinder we can use a Gaussian formula that integral due to surface of side of this cylinder equal Q in over epsilon 0, where Q in is charge inside of this cylinder. And because electric field is radial, we have this Gauss formula equivalent to this formula, that electric field multiplied by side area of this cylinder equal to linear charge density inside of this cylinder multiplied by length of this cylinder and divided by epsilon 0. From here we can find what is electric field. So electric field equal lambda inside of this cylinder and divided by 2 pi r epsilon 0 and multiplied by unit vector r radial to this construction. And now we can write solution for applied electric field in this form, because for radius less than a, linear charge equals 0. For radius between a and 4a, linear charge is lambda, and for radius greater than 4a, again linear charge cancelled equals 0. But because we have dielectric in field between 2a and 3a, we have electric field there reduced by factor k. And finally we can write this solution. So finally electric field equal this expression in 5 different regions. That's the solution for question A. Now let's analyze this result from point of how could we get this result. Because we have a real electric field equal this one. It means that the electric made a charge redistribution it was produced induced charge on inner radius and induced charge in outer radius of this dielectric surface. And to get this kind of electric field, we need to put linear charge density on inside surface of this dielectric. That will be negative lambda I, where lambda I equal 1 minus 1 over k lambda. And on the outside surface of this dielectric we have linear charge density lambda I. This is how we can get this result for electric field. And this we need to solve question B, because now this dielectric will rotate and this linear charge will produce electric current, which can produce a magnetic field. Let's do question B. So for question B, we just found that the electric produced linear electric charge density on outside surface radius 3a lambda I, which is equal to this one, and on inside surface with radius 2a we have a linear charge density negative lambda a. When we rotate this dielectric with the angular speed omega, we will get kind of solenoid. Due to symmetry, we can expect that magnetic field outside of this dielectric will be 0, and inside in radius less than 2r that will be 0 again, and that will go parallel to this cylinder inside of the electric, means between radii 2a and 3a. And we can construct Amperian loop where we have a rectangle with one side parallel to cylinder on distance r greater than 2a and less than 3a, and other side is far away from this cylinder where magnetic field is 0. In that case we can write Ampere law, and on this loop we have this equation. This linear integral must be equal μ0 multiplied by current through this loop. It means that this integral equal PL, which is equal μ0 I in, and I in equal lambda I multiplied by omega L over 2 pi. Now we can count what is magnetic field inside the dielectric. And finally we have a magnetic field inside of this dielectric equal this expression, and outside it's equal 0.